Hello and welcome to the chapters on electromagnetism. Electromagnetism is one of the four fundamental forces and is probably more prevalent in your day-to-day life than gravity, even though gravity is what keeps us connected to the Earth. It is not a very powerful force, and all of our modern life is based on our understanding of electromagnetism. To start out with, we are going to start with electrostatics because electromagnetism can be broken up into two kinds of forces, electricity or electric fields and magnetic fields, and electric force and magnetic. We're going to start out with Coulomb's law, which follows a force similar to the force of gravity. F equals k q1 q2 over the distance squared. Whereas gravity follows the equation F equals g m1 m2 over distance squared, or mass 1 and mass 2. In this case, Q represents the charge of an object which can be positive or negative, unlike mass, and is given by the units of coulombs, or C. Like charges repel like charges, shown by having a positive force, while unlike charges will attract each other, having a negative force. So if Q1 is negative and Q2 is positive, then you will have a negative force. If both are negative, then you have a negative number times a negative number, which will give you a positive force. K is also given by 9 times 10 to the ninth Newton meters squared per Coulomb squared. And this is a very large value compared to G, which was uh, billions and billions times smaller than this. If, for example, a pair of like charges, particles of 1 coulomb each were 1 meter apart, the force of repulsion between them would be 9 billion newtons. That would be more than 10 times the weight of a battleship. So, why do we mainly only see this in very small things, such as current going through a wire or the charges rotating around a nucleus and electrons rotating around a nucleus? That's because they have the two types of charges. So overall, most things that we see are going to have an equal number of positive and negative charges and cancel each other out. So when we look at planets, they feel the pull of gravity, even though gravity is much, much smaller than the electrostatic force. Again, likes repel likes and dislikes attract. So positive and positive charge will repel each other, a negative and a negative charge will repel each other, while a negative and a positive charge will pull each other together. The electrostatic force is also one of the forces that keeps an atom together alongside the strong and weak nuclear forces, but notably not really gravity, because as I said, gravity is very weak compared to the force of electrostatic force, and it only becomes really apparent when you have large numbers of masses, such as the sun or the moon or the earth. For an atom, every atom is composed of a positively charged nucleus surrounded by negatively charged electrons. The electrons of all atoms are identical. Each has the same quantity of negative charge and the same mass. Protons and neutrons make up the nucleus. The common form of the hydrogen atom, which has no neutron, is the only exception. Protons are about 1,800 times more massive than electrons, but they can carry an amount of positive charge equal to the negative charge of electrons. Neutrons have slightly more mass than protons and have no net charge. Atoms usually have as many electrons as protons, so the atom has zero net charge, which is why when you add all the atoms up, they don't have electric forces acting on them, but they do have gravitational forces because you're adding up a bunch of neutral charges or neutrally charged atoms, while each one has a mass that is going to eventually add up to be something very large. When two atoms get close together, the balance of attractive and repelling forces is not perfect because electrons whiz around the volume of each atom. The atom may then attract one another and form a molecule. In fact, all chemical bonding that holds atoms together to form molecules are electrical in nature. When the nucleus was discovered in 1911, scientists knew that electrons couldn't orbit placidly around the nucleus in the way the Earth orbits the Sun. In only about 100 millionth of a second, according to classical physics, the electron would spiral into the nucleus, emitting electromagnetic radiation as it did so. So a new theory was needed. The theory was called quantum mechanics, and is something that we're going to get into in later chapters. Why don't the protons in the nucleus mutually repel and fly apart? What holds the nucleus together? The answer is that in addition to electrical forces in the nucleus, even stronger non-electrical nuclear forces hold the protons together and overcome the electrical repulsion. We will learn about the nuclear forces and how neutrons put a needed distance between the protons in Chapter 33. Interestingly, any electrically charged object has an excess or deficiency of some whole number of electrons, meaning the charge of the object is a whole number multiple of a charge of an electron. Electrons cannot be divided into fractions of electron. Charge is grainy or made of elementary units called quanta, where quanta means that there is only certain numbers of allowed values for the charge. We say that charge is quantized, with the smallest quantum of charge being that of the electron or proton. In all matter, no smaller units of charge have ever been observed. All charged objects to date have a charge that is a whole number multiple of the charge of a single electron or proton. The SI unit of electric charge is the coulomb, abbreviated C. It turns out that 1 coulomb is the charge associated with 6.25 billion electrons. This might seem like a huge number of electrons, but represents only the amount of charge that flows in a common 100-watt light bulb in a little over a second. Mhm. So how do we see this electric charge at a macroscopic or large scale? It is easy to establish an electric current in a metal because one or more of the electrons in the outer shell of its atoms are not anchored to the nuclei of particular atoms but are free to wander in the material. Such a material is called a good conductor, and through that we are able to cause there to be a conduction of electrons through the material and to see the shape or the properties of an electron through its movement through the material. The electrons in other materials, rubber and glass, for example, are tightly bound and belong to particular atoms. They are not free to wander about among other atoms in the material. Consequently, it isn't easy to make them flow. These materials are poor conductors of electrical current for the same reason they are generally poor heat conductors. Such a material is called a good insulator. A material can be made to behave sometimes as an insulator and sometimes as a conductor. This is called a semiconductor. Thin layers of semiconducting materials sandwiched together make up transistors, which are used to control the flow of electrons in circuits, to detect and amplify radio signals, and to produce oscillation in transmitters. They also act as digital switches. These semiconductors and these transistors are only possible to understand through quantum mechanics. So we are going to go over them in a very vague way until we get to quantum mechanics, and then we're probably not going to go over them that specifically. But transistors are the backbone of your computer being able to make decisions or to do calculations. And that is why we needed to develop quantum mechanics in the 20th century before we were able to have complex computers. Remarkably, in certain materials, at sufficiently low temperatures, electrical resistance disappears. This materials acquire zero resistance, infinite conductivity to the flow of charge. Such a material is called a superconductor and also has other interesting properties such as the expulsion of magnetic fields. So how do you charge a macroscopic object if generally they have no net charge? Well, one way is to get something that does have a net charge, such as a glass rod that's been rubbed against a piece of felt or a piece of animal fur in order to acquire a number of electrons, which are negatively charged. And then use that charging by induction to pull all of the positive charges towards the negatively charged rod and pull off the negatively charged, push off the negatively charged charges away. Then, when you separate the two objects, as you see in part C, you will get an object that is positively charged and an object that is negatively charged. There is also something called grounding, where if you take an object and have the charges separated in this way, then you can touch the object and provide a place for the net charges to go, for the unbalanced charges to move away. This is called grounding because you touch the object and it goes through your body to the ground. This causes there to be a positive charge. Charging by induction occurs during thunderstorms. The negatively charged bottoms of clouds induce a positive charge on the surface of the ground below. Benjamin Franklin was the first to demonstrate this with his famous kite flying experiment, proved that lightning is an electrical phenomenon. Lightning is an electrical discharge between a cloud and the oppositely charged ground or between oppositely charged parts of clouds. Franklin also found that charge flows readily to or from sharp metal points, and he fashioned the first lightning rod. The primary purpose of the lightning rod is to prevent a fire caused by lightning. If for any reason sufficient charge does not leak from the air to the rod and the lightning strikes anyway, it may be attracted to the rod and take a different path to the ground, thereby sparing the building. What we saw when we induced a charge is something called polarization, where even if something is net neutral charge, it can have a positive value towards one end and a negative value towards the other if you apply some force pulling the object apart. This occurs naturally in certain molecules, most notably water, which has positive charges on the hydrogen atoms and a negative charge on the oxygen atoms. So if you put a charged rod towards a stream of water, towards water coming out the tap, for example, it will pull the oppositely charged side of the water molecules towards it, and you'll see the stream actually bend towards the rod. So I brought up the presence of electric fields before, but just as the space around a planet and around every other massive body is filled with a gravitational field, the space around every electrically charged body is filled with an electric field, an energetic aura that extends through space. So the electric field, like little g, is defined as the gravitational force divided by the mass of an object. The electric field E is defined as the force from the electrostatic force divided by the charge of an object. So it is this force that would occur if you were to place 1 coulomb of positive charge at a certain point in the electric field. We can also draw out these types of force fields or these electric fields as electric field lines, where a positive charge is going to point out radially in all directions because one positive charge is always going to push a positive charge away, uh, according to the Coulomb's law. Whereas if you have a positive charge and a negative charge together, you have a more complex field lines because the positive charge will push the positive charge of your test charge away, while the negative charge will pull the positive charge of your test charge towards it. And it's going to give you the field lines that you see in part B. And then if you have two plates where one plate is positively charged throughout and the other plate is negatively charged throughout, you see straight lines going from one plate to the other plate as the positive plate would push your positive test charge away, and the negative plate would pull your test charge towards it. In addition to this electric field, there is also electric potential. When we studied energy in Chapter 7, we learned that an object has gravitational potential energy because of its location in a gravitational field. Similarly, a charged object has potential energy by virtue of its location in an electric field. Just as work is required to lift a massive object against the gravitational field of Earth, work is required to push a charged particle against the electric field of the charged body. This work changes the electric potential energy of the charged particle. One electric potential is equal to the electric potential energy divided by charge, which is 1 volt, which is the unit of electric potential, is equal to 1 joule per coulomb. And the electric potential is similar to the electric field in that it is divided by the charge in order to talk more generally about what potential is acting without calculating the potential energy of every single charge in the object. It is also interesting that because conductors are able to move charges around freely, they will also do something called electric shielding, which is that because a conductor is able to move charge around freely, it will rearrange charge until there is no net force on it, meaning that there is no electric field inside of a conductor. It will just rearrange charge in whatever shape is necessary in order to create no electric field inside the conductor. This also means that any surface of the conductor is going to be at the same potential energy or the same electric potential as any other point on the surface. An important difference between electric field and gravitational fields is that electric fields can be shielded by various materials, while gravitational fields cannot. The amount of shielding depends on the material used for shielding. For example, air makes the electric field between two charged objects slightly weaker than it would be in a vacuum, while oil placed between the objects can diminish the field to nearly 1/100th of its original strength. Metal can completely shield an electric field, as I said in the last slide. Quite interestingly, when no current is flowing, the electric field inside a metal is zero, regardless of the field strength inside. If there was an electric field, then the force of the electric field inside of a conductor would cause the charges to move, and they'll move until they're balanced out so that there is no force acting on the object. So for the right side, you see something called a Faraday cage, which is when you are placed inside of a cage or a metal cage, it is going to redirect the electric field or redirect the charges so that electricity will not pass through the cage. This is also going to stop electromagnetic radiation, which we talked about in a previous chapter, and which is used by our phones to make calls from penetrating or getting out of the cage, so you aren't able to make a call when you are inside of a Faraday cage. Finally, I'm going to talk a little bit about capacitors, which is a way to store energy. So if you set two metal plates up against a battery, one of the plates is going to get negative electrons from the negative end of the battery, and the other side of the plate is going to lose electrons and get a net positive charge from the other side of the battery. This is going to create an electric field similar to the electric field that we saw in part C of what we were looking at, the electric field lines. And it's a way of storing energy. So even though there is no net charge, there is no force in between them, because there's no charges in between them, there is an electric field And that electric field is where energy for electromagnetic radiation is stored, as well as the magnetic field, which we are going to get into in subsequent chapters.